Open any standard trigonometry textbook, and you will eventually hit a wall. Pages packed with nearly 40 separate formulas, requiring the memorization of every possible way that sines, cosines, and tangents interact. You do not need to memorize that list. The entire system can collapse down into a single mathematical engine, driven entirely by basic algebra. This equation calculates the sine of two combined angles. It takes the first angle, alpha, and the second angle, beta, and evaluates them through two cross products, the sine of alpha times the cosine of beta, added to the cosine of alpha times the sine of beta. By understanding how this specific engine operates, you replace the rote memorization of 40 rules with a logical process of algebraic substitution. We start by testing the boundaries of the engine. What happens when the two angles inside the formula are exactly the same? If we set the second angle equal to the first, we replace beta with a second alpha. On the right side, we now have sine alpha cosine alpha added to cosine alpha sine alpha. The terms are identical, so we combine them to get 2 sine alpha cosine alpha. We can verify this immediately. If we plug in 30 degrees for alpha, the right side becomes 2 times 1/2 times the square root of 3 over 2. The math evaluates cleanly to the square root of 3 over 2, which is exactly the sine of 60 degrees. Setting the variables to be identical lets us scale angles upward instantly. We rely entirely on algebraic addition without introducing any new geometric definitions. To find a triple angle, we apply that same recursive logic. We simply split 3 alpha into 2 alpha plus a single alpha. We feed that addition back into the engine, generating sine 2 alpha cosine alpha plus cosine 2 alpha sine alpha. We swap the 2 alpha terms for their specific formulas. Distributing the multiplication, we group like variables and collapse all terms to get the final triple angle identity, 3 sine alpha minus 4 sine cubed alpha. Any larger multiple, like finding a quadruple angle, is generated by repeating this exact cycle of substitution and expansion. We can also run the algebraic rules in reverse. By isolating variables, we can calculate the trig values for fractions of known angles. This is the standard cosine double angle formula. If we define x as alpha over 2, we rearrange terms to isolate the sine of the half angle. We take the square root of both sides to remove the exponent. Notice the plus or minus symbol in front of the root. Selecting positive or negative is a practical choice. You evaluate which specific quadrant the target half angle sits in and apply the correct sign for that region. Running the algebraic manipulation backward allows for the calculation of smaller fractional angles, governed only by basic quadrant geography. When moving into advanced physics and calculus, adding two trigonometric functions together is often a dead end. You need a way to multiply them instead. Here is the sine addition formula stacked on top of the sine subtraction formula. We vertically add them together. Because the right sides have opposing signs for the second term, they perfectly cancel out. This leaves a clean multiplied product, 2 sine alpha cosine beta. Transforming an addition problem into a multiplication problem requires 0 geometric tricks. It is just the vertical cancellation of stacked equations. Look at this fraction. It asks us to divide the difference of 2 signs by the sum of 2 signs. Using our sum to product rules, we translate the top and bottom simultaneously, turning the messy addition and subtraction into clean multiplication. Now we can reduce. The 2's cancel, sine over cosine becomes tangent, and cosine over sine becomes cotangent, which rearranges into a final ratio of tangent half angles. Visually intimidating fractions simplify rapidly once you apply methodical algebraic substitution. Over 30 distinct rules are generated from one single starting point, entirely by pushing, pulling, and stacking the base equation. This map shows the complete logical flow. From the core engine at the top, you can branch downward to derive every category of identities. Solving these problems comes from understanding structural connections. Once you know how the engine is built, you never have to rely on rote memorization again.